Welcome all. In this particular lecture, we are moving on to the last part of engineering mechanics syllabus, that is closed and open coiled springs. So as we all know, spring is a elastic machine element which deflects under the action of load. So whenever load applies on a spring, it will deflect and it returns back to its original position when we are removing the load. So this is the activity of a spring, and it is used normally for absorbing shocks and vibrations. Normally in the seats of vehicles and wherever vibrations are there, possible vibrations are there, we will provide spring as a machine element. So in case of vehicle suspension system, springs in clocks and toys, balance, cam and followers, in all the cases we will provide springs as one of the machine element. The quality of a spring is judged by the energy it can absorb. The absorbed energy is used for absorbing absorbing the vibrations. Okay. Now there are important terms which are related to spring. One is resilience. It is a common term used for the total strain energy stored. The total energy stored in a spring is known as resilience, and it is also explained as the capacity of a strained body for doing work. The capacity of a spring to do work is also known as resilience. It is the total energy stored in the spring. Now another important term is stiffness. It is a load required to produce a unit deflection in a spring. So whenever we are applying a load, there will be deflection in the spring, deflection in the length or width of the spring, and that particular deflection per unit load, the load required to produce a unit deflection. For example, if 1 centimeter deflection is there, how much is the load which causes that deflection? That is known as stiffness of a spring, how much stiff the spring is. Now there are different types of springs. Normally there are bending springs and torsion springs. The springs you may have seen. These are known as bending springs. Mainly these are used in carriages such as vehicles, lorries, etc., railway wagons, etc. And this is subjected to bending only. So this the shape of the spring itself we can uh, explain. We can say that the shape of the spring itself is an example, or it is a um, thing which represents that it could absorb bending, or it could withstand bending. So the resilience of this particular spring, or the energy carried or energy absorbed by the spring, is also due to bending. Okay. These are otherwise known as laminated spring or leaf spring. Laminated, or laminated means there are many number of layers are there. It is also known as leaf springs, mainly used in railway wagons. Another type of spring is known as this springs which you have commonly seen. These are known as torsion springs because it is in the shape of a circle and twisted into a number of coils. So these are known as torsion springs. It is subjected to torsion or twisting moment only, and the resilience is also due to the torsion. So it is otherwise known as helical springs. Helical springs, since it is bent into a helical shape, and they are subjected to torsion as well as bending. They can bend as well as twist. Okay. So mainly the main categories of springs are laminated springs and torsion springs. Sorry, that bending springs and torsion springs. Out of that, the commonly used springs for engineering practices is carriage springs or leaf springs, which we have already discussed as bending springs, and helical springs, which we have already discussed as torsion spring. The technical terms used for the springs which we are using in engineering practices is these two. So the first one is carriage spring or leaf spring. They are again classified into semi-elliptical and quarter elliptical. You can see the picture. This is a semi-elliptical spring because ellipse is the shape. This is the shape of an ellipse. Half of that is semi-elliptical. Now quarter of the ellipse up to this portion only, that is known as quarter elliptical. Now, the semi-elliptical springs are normally supported at its end, subjected to central load, that is simply supported. It may be found in the form of a simply supported structure, and quarter elliptical may be cantilever. At this point it will be fixed and the other point will be freely given. These springs are normally used in railway wagons, coaches, etc. These laminated springs or the carriage springs or the leaf springs, they are used to absorb shocks which gives us unpleasant feeling to the passenger, and this the energy which is stored in this particular springs will be released without doing any particular work because it is just to absorb the unpleasant vibrations. Okay. It consists of a number of parallel strips. Layer by layer, the number of strips are there, which is having a larger diameter at the top end, and the diameter will be decreasing at the bottom end. It will be very less. So this is known as a laminated spring, leaf spring, or a carriage spring. The second thing is helical spring. Helical spring is in the form of a helic. They are of two types, closely coiled and open coiled are there. This is an example of an open coiled spring. So this is close coiled. We'll move on to close coiled helical springs first. These the difference between open and close coiled is in close coiled spring the uh, coils are very closely, there will not be any space between two coils, so the coils are very closely spaced and it is in the form of a helix. The bending stress is negligible as compared to the torsional stress here because there is no space for bending. So bending stresses are very negligible. Torsion is there because we are twisting it and increasing the turns. So that's it. So we have to see two cases, two types of loads which may possibly be occurring on a spring. One is an axial load and other one is an axial twist. So we'll see both the cases. First, a close coiled springs with axial loading. So this is a close coiled spring which is acted by an axial load, that is W, which will be like this. The load will be like this. The distance, the radius of the helix is capital R. The diameter of the wire which forms the helix is D, small letter d. C is the modulus of rigidity, W is the axial load, tau is the maximum shear stress induced in the wire due to twisting, theta is the angle of twist. Theta is the angle of twist of the spring, delta is the deflection. Delta is the deflection of the spring as a result of axial load. So if we are providing an axial load here, there will be some deflection in the length. So that is known as delta, and theta is the angle of the twist. How much angle it will be twisted. So these are the things, and n is the number of turns of the coils. Now the total load will the load which we are providing here will cause a twisting moment. Got it? So it will cause a twisting because we are applying the load here. So what will happen is this coil will become tight and it will twist the particular spring. So that twisting moment will be equal to load into perpendicular distance. Load is W, the perpendicular distance is R. So twisting moment is W into R. Now the twisting moment can also be written as for a circle. It forms a circle, right? When we are seeing the plan view of a spring, it will be a circle. So for a circle, the twisting moment is pi by 16 tau d cube. So that means we have already discussed this one in one of the lecture number 20. You have discussed this thing. T is equal to pi by 16 tau d cube for a circle. Now this T will be equal to WR. So WR is equal to pi by 16 tau d cube. Now the length of the wire, the total length of the wire is nothing but the length or the perimeter of each circle which is forming into the number of circles. The perimeter of the circle is nothing but it is 2 pi r. 2 pi r is the total perimeter of one circle which is forming. Now how many number of circles are forming? N number. So 2 pi r into n is the total length of coil. Total length of coil. Length of one coil into number of coils. Now in the lecture 20 we have already seen the torsion equation. So for a circular shaft the torsion is T by J is equal to C theta by L, the equation for torsion. So from that theta is nothing but it is an angle of twist. Theta is TL divided by JC. In that T we have already seen in this particular equation it is equal to pi by 16 tau d cube. So that value we have to provide, or otherwise we can provide W into R. Here you can see T is equal to W into R. So T is W into R, L is nothing but it is 2 pi Rn, J is the, what is that J? Polar moment of inertia. Polar moment of inertia is pi by 32 into d raised to 4 for circle. So pi by 32 into d raised to 4 we have taken, and C is a constant C. So we have taken. So when simplifying this you will get 64 W R square and divided by C d raised to 4 is the angle of twist. How much angle it got twisted. Now the deflection, because of this angular twist, a deflection occurs to the spring, right? Deflection from the original position occurs. That deflection is nothing but R into theta. R into how much is the angle of twist, that is the deflection. So R into the value of theta we have already seen here. So R into theta will give you 64 W R cube and divided by C d raised to 4. Now the total energy stored in the spring is nothing but half into load into deflection, half into W into tau. Tau is the deflection. Now dou. Now stiffness of the spring is nothing but it is the work or the load per unit deflection. The load per unit deflection is known as stiffness. So load is W and deflection is C d raised to 4 64 W r cube and divided by C d raised to, so you will get the stiffness as C d raised to 4 divided by 64 r cube N. So the things to be found out is first the torsion you have to found, how much is the twisting moment, now the length of the coil. Now from the torsion equation you will get the angle of twist. Deflection of the spring is r into theta. Theta is the angle of twist we have already found. Now energy stored is half into load into deflection. Stiffness is load per unit deflection. So this was the first case in which closed coiled helical spring subjected to axial loading. The second case is closed coiled helical spring subjected to angle twist. Axial twist. So we are applying a twist here. Instead of loading, we will apply a twist here. Then the terms we have already discussed is D is here, number of coils N, C is the modulus of rigidity, M is the moment or axial twist applied. Now what will happen if we are applying a twist here? When we are tightening here by means of by the application of a twist, then what will happen? This coil will become tight and the radius or the diameter of the coil will decrease and the number of turns will increase. Okay. If you are loosening the twist means the diameter of the coil will increase and the number of coils will decrease. So when we are tightening it here, the diameter of the coil decrease and the number of coils will increase. So that you have to just assume what is happening when we are providing a twist. Now as in the earlier case, the length of the spring is nothing but it is L is equal to 2 pi r, the length of one circle into number of circles, that is 2 pi rn. Now if you are providing a twist, what will happen? The diameter will decrease and the number of coils will increase. So the new diameter is r dash and the new number of coils is n dash. Let it be. Then what will happen to the length? 2 pi rn is equal to 2 pi r dash n dash. The total length remains same, but the diameter and the number of coils will change inversely. So when r increases, n decreases. So r dash n dash will come. Now from this equation, 1 by r is equal to 2 pi n divided by L and 1 by r dash is equal to 2 pi n dash divided by L. Now since we are applying a bending a moment here, by the bending moment equation, m by I is equal to E by R. We have already discussed that in the lecture number 18. So m by I is equal to E by R is equal to E into change of curvature. E by R is nothing but E into change of curvature, that is E into 1 by R dash minus 1 by R. 1 by R dash is nothing but it is 2 pi n divided by L and 1 by 2 pi n dash divided by L, and 1 by R is nothing but it is 2 pi n divided by L. So we'll get it as 2 pi E divided by L into n dash minus n, which is equal to m by I. So ml divided by EI. So this is the equation you will get. Now the angle of bend phi. In the earlier case it was twisting angle. So here the angle of bend phi is equal to 2 pi n dash minus n. ML, because ml divided by EI is nothing but it is the angle of bend. 2 pi n dash minus n is nothing but it is the angle of bend. So angle of bend is nothing but ml divided by EI. Now we have to differentiate this particular equation with respect to dl for getting the total change. D phi by dl is equal to m by EI you will get with respect to L if you are differentiating. That means the change in the bend or the change in the curvature of this particular coil is not dependent on anything. It is a constant parameter. The curvature will, so even if you are tightening this, അതായത് നമ്മൾ ഇതിനെ മുറിക്കാലും ഇതിൻ്റെ ഈ curvature, അതായത് ഈ ചരിവ് എന്ന് പറയുന്നത് it will be same, it will be a constant. The only thing is ഇതിൻ്റെ diameter കുറയും, number of coils കൂടുമെന്നല്ലാതെ ഇതിൻ്റെ curvatureന് വ്യത്യാസമൊന്നും ഉണ്ടാവില്ല. Why? Because when we are differentiating it with respect to length, you will get a constant at the right. M is a constant, E is a constant, I is a constant. So m by EI is also a constant. So that means curvature is not changing. The change in curvature or angle of bend per unit length is constant throughout the spring. Now, so this is about the angle of bend. Now the energy stored in the spring is nothing but it is half into bending moment into phi. Bending moment into phi. In the previous case it was half into W into delta. Now we are moving on to the open coiled spring, the second case. For an open coiled spring, D is the diameter of the wire which we are using. P is nothing but it is a pitch. From the center of this wire to the center of the other thrust, it will be pitch. This is R and this is the loading W. So for axial loading for an open coil spring, alpha is nothing but the angle of the helix. So this angle is known as alpha. For the closed coiled spring, it was not there. For open coiled spring, there is an angle of helix angle. Now in this open coiled spring, what the case is, we'll get both torsion as well as bending moment. Okay, bending as well as twisting occurs in this particular case because it is open coiled. Bending means um, the change in this particular thing occurs, twisting also occurs. So twisting is nothing but it is WR cos phi because twisting occurs in this particular direction, WR cos phi, and bending in this direction, so it is WR sin phi. So this causes twisting of the coils and this causes bending of the coils. Now the angle of deflection of the spring is delta. Deflection is nothing but the change in the diameter. Phi is the angle of twist. How much is the twist occurs? Phi. Sorry, not theta. Theta is the angle of twist and phi is the angle of bend as a result of bending moment. Now the length of the spring, the length of the wire is 2 pi Rn into sec theta. How the sec theta will come? Because we have to provide uh, that by taking this triangle you will get uh, phi that 2 pi r as sec theta. R sec theta component should be taken for getting that L, that you can solve by means of the trigonometrical calculations. It is r sec theta, you'll get, you take this particular triangle and solve it. So 2 pi r and sec theta. Now the twisting moment is nothing but WR into cos phi. In this case you have already seen twisting moment is WR cos phi, which is equal to pi by 16 into tau d cube. We already know twisting is pi by 16 tau d cube. So WR cos phi is pi by 16 tau d cube. Now bending stress is nothing but it is My by I. From in the previous equation, that is in the lecture 18 we have already seen bending moment equation is My by I. So M is nothing but WR sin phi. Y is nothing but D by 2. D by 2. Y is the distance from the neutral axis to the extreme fiber, that is D by 2. I is nothing but moment of inertia. Moment of inertia for a circular section is nothing but it is pi by 64 d raised to 4. So I'll get the bending stress as 32 WR sin alpha divided by pi d cube. So bending stress you got, twisting moment you got. Now the angle of twist theta is TL by JC as per the torsion equation, which is already explained in lecture number 21, TL by JC. In that T is equal to WR cos phi, cos alpha. L is nothing but L is itself J into C. Angle of bend phi is nothing but ML by EI. M is nothing but WR sin alpha L divided by EI. So angle of bend you got, angle of twist also you got. Now work done. Work done is the total work done by twist as well as bending. So total work done is half W delta, which is equal to twisting work as well as bending work. Twisting work is half T theta plus bending work is half M phi. So you'll get in total we have to provide the value of T and phi, T, theta, M and phi. So finally you will get delta is equal to WR square L into cos square alpha divided by JC plus sin square alpha divided by EI. Now in this particular equation you have to provide the value of L. J is nothing but polar moment of inertia, which is equal to pi by 32 d raised to 4. And L is nothing but L 2 pi r and sec theta. C is a constant. E is also a constant. I is nothing but pi by 64 d cube. So all these values you have to provide, pi by 64 d raised to 4. So all these values you have to provide and finally you will get delta or the change angle, the deflection as 64 WR cube and sec theta divided by d raised to 4 into cos square alpha divided by C plus 2 sin square alpha divided by E. So this is for open coiled spring, the deflection for open coiled spring. When alpha is equal to 0, alpha is nothing but you already knows what is alpha. Alpha is the helix angle of an open coiled spring. For closed coiled spring, this alpha will be 0. So when we are substituting alpha is equal to 0 in this particular equation, you will get the value of deflection for the closed coiled spring. That is 64 WR square and divided by CD raised to 4. So this is about this lecture. In this lecture we have seen two types of springs, closed and open coiled springs. For closed coiled springs there is no angle of helix. For open coiled springs, there is an angle of helix, and we have found the angular twist. Angle of for closed coiled springs, there is only twisting moment occurs. So twisting moment we have found, the angle of helix, angle of twist you have found, the deflection you have found, the energy stored you have found. Now for closed coiled spring, both bending as well as twisting occurs. So twisting angle and bending angle you have found, work done you have found, and the deflection also you have found. So this is about today's lecture. Thank you.